All right. So today's lab is commonly called a precipitation lab, but it really kind of stems around solubility. So let's start there for a second. Has everyone's kind of worked through solubility, right? We have a basic idea of solubility.
Yeah.
Can someone give me a definition of solubility?
Well, it's able to dissolve in a liquid.
Say that again. Say it out loud.
It's able to dissolve in a liquid.
Yes. So that is the ability of a solid to dissolve. One thing I like about solubility is you can make a sentence out of it and basically use the same word like 5 times, like 2 words and 5 times. So like the solubility of a solute is this ability to dissolve in a solvent to make a solution. Like you end up using some form of solute 3 times and some form of solvent you dissolve twice, right? It's just so. It's the ability of a solute to dissolve in a solvent to make a solution, and how much of it dissolves is its solubility, right? So we have some things that are soluble, some things that are not soluble, and that's what this lab is over today. So one of the most soluble salts, and I'm going to tell you this, and you can question me. One of the most soluble salts there is sodium nitrate. Well, you can go, I don't believe you, Dr. Brady, and I can say that's cool. Let's look at the solubility tables on the board. Rule number 1, all group 1 and ammonium compounds are soluble. Group 1 being hydrogen, lithium, sodium, potassium, rubidium, right, cesium. Well, sodium, all sodium salts are soluble. Then you can go to rule number 2. All acetates, all nitrates, all perchlorates are soluble, and there are no exceptions. So here's my nitrate. So you can imagine if all group 1 are soluble and all nitrates are soluble, if you put those together, you get something super soluble, right? One of the most insoluble solids that you can make is silver chloride. And so we can look at the board and we can see whether Dr. Bray is telling you the truth. Rule number 3, all chlorides are soluble, as well as bromides and iodides. Essentially, all halogens, all halides. And there's an asterisk because like a lot of fluorides are, and then it gets, like there's so many exceptions that they don't put fluoride in here. But you can basically say all halides, with the exception of fluoride, are soluble, with the exception of four metals: silver, lead, 2+, copper, 1+, and mercury, 2+. Now, a quick comment about those. I want you to notice that this is copper 1+, and next to it is mercury 2+, right? We're going to come back to that in a second. But you see that all that silver chloride, all chlorides are soluble except for silver chloride. You can go to the solubility table and you see, yep, that's correct. I want to point out while I'm thinking about it, because I might forget downstream, that if you skip down to rule number 5 where it says all thiocyanates are soluble except lead 2+ and copper 2+, that is not a typo. Copper can exist in 2 different oxidation states. It can be 1+ or 2+. It's the 1+ that can't kick it that will precipitate with chloride. It's the 2+ that will precipitate with thiocyanate. And I just want to make sure that you don't think that there's a typo. Also, while I'm thinking about it, this mercury 2+, this is formally mercury 1+. Like, there's 2 of them. Each one is +1, so it's 2+. So as far as an oxidation state, if I was to, this mercury is actually mercury 1. But it's the only compound on the periodic table that I know of that you're going to see in the general chemistry laboratory that exists as what's called a dimer. You'll never find, or you won't find Hg+, especially in your solubility tables. You'll find it as this dimer, meaning there's 2 of them and a 2+. So if I was to write out mercury 1 nitrate, it wouldn't be mercury nitrate. It would be mercury nitrate, like that. And this also is the only time there's an exception in reducing a molecular formula to an empirical formula. So I'm kind of throwing a couple of exceptions in there early because I tend to forget this. Oddly enough, we were working on this problem today, so that's why it was so fresh on my mind. this is mercury 1. If you were to write this out as a compound, it would be mercury 1 nitrate. Super confusing when you see 2 of them in that. Does that make sense? Like this is just one of the, like, if you give me a periodic table, I can tell you just about everything you want to know about a compound. I can tell you how many valence electrons it has. I can tell you what the electronic configuration is. I can tell you whether it has hybridized orbitals. I can tell you what its electronic configuration is going to look like, or electronic geometry. I can give you an idea of what it's, if it's going to have lone pairs of electrons or bonding electrons. I can tell you whether it's going to, what its molecular geometry is going to be. I can tell you whether a bond is going to be polar. I can talk about intermolecular forces. If you give me a periodic table, I can tell you just about anything you want to know about a compound, with the exception of a solubility table. There's nothing that I've found that helps me remember. I've never found like a mnemonic device, an acronym. Do you have one?
Oh, no.
Okay, then.
I was going to say, our chemistry professor wants us to remember the whole thing.
You do, yeah, you have to memorize the whole thing. Now, I will say, even that's kind of hard. Like, what's kind of nice is if you look up there, you can see some of your strong acids up there. So like your nitric acid, your perchloric acid, your hydrochloric acid, your hydrobromic acid, your hydroiodic acid. There's all your soluble compounds. So that, you know, those are your strong acids and those are soluble compounds. Obviously, phosphates down below, so it doesn't cross for all of them. And what's also nice is your exceptions typically track. So silver, lead, copper 1, mercury 1 in the dimer form. For exception number 3, with sulfates, mercury and lead again. With thiocyanate, mercury, but this time copper 2. So there's a little bit that kind of, but even then, like if you look in the periodic table, silver, lead, and copper are not like kicking it next to each other on a row. They're kind of at an angle on the periodic table. All right, so let's go back to here. So you can look at this table, you can say, yeah, that's really soluble. Yeah, that's insoluble. But how would you, let me show you another compound. I kind of find this interesting. And if you want to know what Dr. Braley thinks about when he's laying in bed waiting to go to sleep, it's literally what I'm talking to him in the morning. And I really don't know why. I wish I could control my brain. But, so, magnesium sulfate. Magnesium sulfate. Does anyone know what the commercial use for magnesium sulfate is? Your parents probably have some of this in their house.
Is it a cleaner? Is it a cleaner?
Nope.
You could with it?
Nope. So, anyone ever heard of Epsom salt?
Yeah. Oh.
This is Epsom salt is magnesium sulfate. So Epsom salt makes a great bath, your tired muscles. It makes a great laxative if you're kind of worked up about things and you need things to move a little bit. You got your magnesium sulfate, right? So clearly magnesium sulfate is soluble, right? Well, if you were to take and punch a hole in the wall in most of your houses, what do they use? What are the walls made out of? Not the studs, but the thing on the front. Drywall, right? Drywall, sheetrock. Sheetrock is made from gypsum. Gypsum is a compound that is geologically it's called gypsum. That's what it's called when it comes from the earth. I'm losing the phrase for that. The gypsum is calcium sulfate. So if you look at if you look at rule number 4, it says most sulfates are soluble except for barium, strontium, and calcium. So we just went from the second group, magnesium sulfate, being soluble, to the element below it, calcium, being insoluble. We went from bath salts to sheetrock. You can go one step further, and I don't know, does anyone work in the medical field? Does anyone know what barium sulfate is used in a medical setting? So there's a technique. How many here are pre-med? You're pre-med, you're pre-med, you're pre-med, you're pre-med. Anyone ever heard of a barium enema? Okay, you have. What is a barium enema?
It's a thing, it's like, I don't know. I don't know how to explain it. It's just like
So do you?
it's like a solution.
It's a suspension because it's not because it's all chalky, right?
Yeah.
And then you drink it. What happens next?
Is it like polyethylene glycol?
No, it's like barium sulfate. Barium minima is barium sulfate.
Okay.
So barium sulfate is a chalky mixture, and if you drink it, it's kind of cool. I had one when I was 15 because I had like an intestinal blockage, and I'm laying down. I can't remember if I was laying down or if I was standing up, but I have this like machine, and it's taking an active X-ray of me, and it's just passing through. You can see bones, and that's all I can really see. A little bit of soft tissue, but not much, mostly bones. As I'm drinking the barium, X-rays bounce off of electrons, and the more electrons you have, the more they bounce off of, and barium is like on the 4th or 5th row. 5th row, I think. So there's a lot of electrons around it, and so as I'm drinking it, you can see the barium as it's going down my esophagus, around my stomach, moving through my intestines, and it's just like up on the X-ray. You're just watching, I'm just drinking it, you're just watching it go through, and then it stopped moving, and they're like, oh, there's your blockage. Now we know that you have scar tissue on your intestine. We need to figure out what's going on there. So, like, just with your sulfates, like, insoluble, rule number 4, barium and calcium and strontium, not one of the exceptions, soluble. Now, let's say that you work in the lab, well, you're a hospital system, and you need barium sulfate. So one option would be to go to the barium sulfate mines, unless someone dig up some barium sulfate. But we're chemists. We can make barium sulfate now, right? So one of the ways we can make barium sulfate is we can take magnesium sulfate, and we can. You remember there are 5 types of reactions, and what's up? So there are 5 types of reactions, and I try and make them really easy. I try and make everything easy because I'm not that smart, so I have to make chemistry easy. We're either putting stuff together, taking stuff apart, burning things, or we're switching things out. And we're either switching out one thing or 2 things, right? So you got synthesis, decomposition, combustion, single displacement, double displacement. Put them together, take them apart, burn them, switch one, switch 2. That's all you can do in chemistry, right? So if I want to take and mix something, and if I want to end up with barium sulfate, if we look at that table over here, what could I mix with magnesium sulfate that I can switch out and get barium sulfate? Give me something that barium is soluble with.
Chlorine.
All right, chloride. So you can take barium chloride. Now barium chloride, if we dissolve this up in water, we're going to have an aqueous solution of magnesium sulfate. So I'm going to draw that here. Magnesium sulfate. And we're going to make another little solution of barium chloride, and that's going to be aqueous because it's dissolved in water. And if we take these and mix them in a bigger beaker, you'll have barium sulfide or sulfate at the bottom. And then what else is going to be in there with it?
Magnesium.
What's that?
Magnesium chloride.
Magnesium chloride. So we dissolve up magnesium sulfate, we dissolve up barium chloride, we mix them together, we get a precipitate, and I always distinguish these 2. So it's the same word twice. Precipitate. So as a verb, barium sulfate is precipitating. When we have rain, that's called precipitation. So you have a precipitate as a verb. This is how I do it, because I like to distinguish. As a noun, I call it a precipitate. So precipitates precipitate out a solution, because otherwise, if you don't, it just sounds like you're saying the same word over and over. Okay. So barium sulfate precipitates as a precipitate, and then the rest of it is a solution. This is basically all we're going to do today. We're going to do it 12 times. We're going to do some predictions based upon what's mixing together, whether we think there's going to be a solution come out. Then we're going to kind of get a sense for what the precipitate looks like. And then you're going to have an unknown. And then you're going to mix those together, and you're going to use these solubility tables like Sherlock Holmes over here, and you're going to deduce what your unknown is. What you got?
How do you know just by looking at a balanced equation if it will, something that will precipitate or not? Is it just by memorizing this table?
Yeah. Well, I mean, at my stage of the game, I usually just look it up. But at your stage of the game, it's because you're going to memorize it. So the way that you would do it, I mean, when I was in graduate school, they made us memorize the periodic table, but I can't do that anymore either. Like, too many brain cells are dead in my head. What I usually do, if you give me a reaction, I'm just going to scan it with my eyes. And the first thing I'm going to do is I'm going to take these two cations and I'm just going to like mentally switch them out. Magnesium sulfate, barium sulfate. Oh, sulfate, exception, barium, precipitate. Barium chloride, magnesium chloride. Oh, like very quickly you can do this in your mind. And then you'll either get the reaction, which we saw, barium sulfate, or you'll get no reaction. So like if we were to put ammonium nitrate and sodium acetate together, I can switch those out all I want, but all acetates, all nitrates, ammonium, and sodium, they're all soluble. So they're not gonna, you can switch it ain't gonna do anything. That'd be a no reaction. You know, if I just did ammonium nitrate, that's a good way to blow stuff up. Plus like sodium chloride. In this context, there wouldn't be a reaction. It would just, it'd either be no reaction, depending on the parameters of the question, there would either be no reaction, or it's just gonna be the same thing.
So it depends on the, like, if it's aqueous or not. If everything's aqueous, there's not going to be.
Well, you're assuming everything's aqueous. So whenever we were doing the copper lab, all the chemistry was happening on the surface of the copper. You had copper metal, then you had copper chloride salt, dissolved in solution aqueous, and then you had aluminum metal. All the chemistry was happening on the surface. And the aluminum didn't become soluble until it oxidized. Yeah, until it oxidized, became aluminum chloride and it floated off in solution. So when you talk about solubility reactions, this is what we're talking about. So we have our, let's go back to this reaction. So we have our reaction. Now, you know, there's probably a lab professor who's not as tall as me, gets down to me every week for putting that thing out there. So this is what we call a balanced molecular formula. Now, it's not busted out into ions because it has the word aqueous behind it. And aqueous means dissolved in water. You can look to see that these are metals and polyatomic anions, which means they dissociate. So this reaction tells you that you have ions in solution, right? So we don't, but it's written as the molecule. So it's like as the molecule dissolved in, this molecule dissolved in water plus that molecule dissolved in water will give that precipitate and that thing dissolved in water. Now, what the next step you have to do with it, that you typically do is it's either called a total or complete ionic equation. So this is where you would break it up into magnesium 2 plus aqueous plus sulfate 2 minus aqueous plus barium 2 plus aqueous. And I'm a stickler. The number, I've said it before, I'll say it again, the number always comes first. It's never magnesium minus 2. That is not correct. It's magnesium 2 plus. Barium 2 plus 2 chloride aqueous goes to barium sulfate. Try as I might, that's still going to be a solid. There's no ions here. I mean, there are, but there's no ions dissolved in solution. Plus magnesium 2 plus 2 chloride aqueous. So this is a total or complete ionic equation. And really, these two things say the exact same thing. Can y'all see that? Like, all I did was take a short sentence and make it longer. Because I just dissociated all my ions, right? Make sense? And if I had a second pen, which I don't. All right. Now, the next thing that that we're typically asked is what's called a net ionic equation. So, if you get paid $20 an hour and you work 40 hours a week, that's $800, right? But you don't make $800. The government takes about 20% of that, right? That becomes your net pay. It's your pay minus you take out whatever ain't yours, right? Well, whatever the government deems 8 hours. What's up?
So for the total complete, the reason you don't separate the precipitants in?
No.
Okay.
No, because it's not. Because it exists as a molecule now. Like, it's not barium sulfate flying around. It is barium sulfate as a clump in the bottom of that beaker.
Okay.
Right? Now there's still barium ions and sulfate ions, but they haven't dissociated. They can't dissociate in solution because they're insoluble.
Okay.
This is pretending they're all in the same beaker now. This guy's not going to become aqueous. He's not going to spread apart.
Okay.
So the next thing we do is we write a net ionic equation. And the way we do that is we get rid of anything that's on both sides of the periodic table, or both sides of the equation. All the chloride, all the magnesium, and whatever you're left over with, that becomes the net ionic equation. What you end up taking out, these are called spectator ions. So one way to think about it is that the only thing magnesium did was act as a carrier for sulfate. And then after that, it doesn't do anything else, it just floats around solution. And then chloride just acts as the balancing ion for barium, and it's just floating around a solution. They don't have any real, they didn't drive the precipitation. We could have done barium nitrate, we could have done barium acetate. Like, it doesn't matter, that anion is useless at this point because all it did was get barium into the beaker. So you have your net ionic equation, and that's when you, I usually do my cation first. All right, this says, if I dissolve barium ions in solution, I don't really care how it gets there, and sulfate ion solutions and sulfate ions in solution, don't care how they got there, I'll precipitate that out. And this is something that, maybe a chemist be like, well, I know if I can get some barium sulfate together, I can make some barium sulfate. Do you have any barium salts? Do you have any sulfate salts? Like, you can start putting together a chemical reaction if you know the solubility part. So the only other thing that can be kind of confusing here is I randomly picked magnesium sulfate and barium sulfate because it tells a good story, and I like to talk about bathroom humor and hospital humor or stories. But if I would have used, say, sodium sulfate, plus barium chloride, I'll still get barium sulfate, but I'm going to get sodium chloride, right? Oops, solid. So is this a balanced chemical equation?
No.
Why?
You need
You need to put
two.
two in
You need a
parentheses.
coefficient of 2.
Right here?
Yeah.
Put a 2 here?
Yeah. Okay.
All right. So when you do these kind of reactions, if someone gives you that part, you got to be savvy enough to break them apart, and whenever you form it, know what's going to form. So if you're doing like sodium sulfide, which is Na2, like, you can't just assume that there's 2 sodium ions floating around. You have to know that wherever you come out on the other side has to be a correct chemical equation, a chemical formula, and it has to be balanced with the coefficient, so you have a balanced chemical equation. So that is effectively all the chemistry that we have to do today. And we're going to do it basically 18 times. All right? Are there any questions about these concepts? What's up, Lucas?
Did you cross out for the total complete equation? Did you cross out the? Is it because those two are the only ones that make it solid? Is it because the product is solid that the other two are spectators?
They're spectators because on both sides of the equation, they're dissolved ions. It's a dissolved ion on both sides. So the fact that it dissolved, in my mind, says that all chloride did was help barium get into the solution. All magnesium did was help sulfate get into the solution. And after they did that, they just stood back and let the magic happen. And then barium sulfate popped out. But at the end of the day, these things are still there.
But just from looking at the molecular formula, how would you know that barium sulfate formed but not the other?
Your solubility tables.
That's true.
This is where you have to know your solubility tables. And that's why we're doing this lab, is to help you, to give you an opportunity to do something where you're holding a test tube in your hand to learn a solubility table. You're gonna do it 18 times. All right? So,